Thyristors, and their types and functions. Thyristors are a class of semiconductor devices that act as switches, controlling large amounts of power with a small input signal. They are used extensively in power electronics and can be found in applications like motor control, power supplies, and light dimmers. Here are the main types of thyristors. The silicon-controlled rectifier, SCR, is a type of thyristor used extensively in power electronics for controlling high voltage and current. It is a 4-layer semiconductor device that acts as a switch, conducting when a gate signal is applied and continuing to conduct until the current through it drops below a certain threshold. Structure and operation. Structure. Layers. The SCR consists of 4 layers of alternating p-type and n-type material, forming a p-n-p-n structure. Terminals. It has 3 terminals. Anode, A connected to the outer p-type layer. Cathode, K connected to the outer n-type layer. Gate, G connected to the inner p-type layer. Operation. Off state, blocking state. When no gate signal is applied, the SCR remains in a high resistance state, blocking current flow from the anode to the cathode. On state, conducting state. When a small current is applied to the gate, it triggers the SCR, causing it to switch to a low resistance state and allowing current to flow from the anode to the cathode. Once triggered, the SCR continues to conduct even if the gate signal is removed, as long as the current through the device remains above the holding current. Turn off. The SCR can be turned off by reducing the current through it to below the holding current. This can be achieved by interrupting the current flow or by using an external circuit to reduce the current. Key characteristics. Latching device. Once triggered, it remains in the conducting state without needing continuous gate current. High voltage and current ratings, suitable for applications requiring control of large amounts of power. Unidirectional, conducts current only in one direction, from anode to cathode. Gate sensitivity, requires a small gate current to trigger. Applications. Power control, used in AC and DC power control applications, such as motor speed controls, light dimmers, and heating controls. Rectifiers, employed in controlled rectifiers for converting AC to DC with adjustable output voltage. Inverters, used in inverter circuits to convert DC to AC. Overvoltage protection, provides protection in power circuits by crowbarring the circuit during overvoltage conditions. Advantages. High efficiency, minimal power loss when in the conducting state. Robustness, can handle high voltages and currents. Simplicity, easy to trigger with a small gate current. Limitations. Unidirectional current flow, cannot be used for bidirectional current control without additional components. Requires commutation circuit. For turning off the SCR, especially in DC applications, an external commutation circuit is needed. Slower switching speed, compared to other semiconductor devices like MOSFETs or IGBTs. Understanding the operation and characteristics of SCRs is essential for designing and implementing power control circuits effectively. The gate turn-off thyristor, GTO, is a type of thyristor that can be turned on and off by applying a gate signal. Unlike the traditional SCR, which requires the current to fall below a holding level to turn off, the GTO can be actively turned off by a gate signal, offering greater control over power switching. Structure and operation. Structure. Layers. Similar to the SCR, the GTO has a 4-layer p-n-p-n structure. Terminals. It has 3 main terminals. Anode, A connected to the outer p-type layer. Cathode, K connected to the outer n-type layer. Gate, G connected to the inner p-type layer. Operation. Turn on. When a positive gate current is applied, the GTO turns on, allowing current to flow from the anode to the cathode. The device enters the conducting state and behaves similarly to an SCR in this state. Turn off. To turn off the GTO, a negative gate current is applied. This removes carriers from the junctions, interrupting the current flow and turning the device off. The turn-off process requires a substantial negative gate current, often a significant fraction of the anode current. Key characteristics. Bidirectional gate control, can be turned on with a positive gate current and turned off with a negative gate current. High voltage and current ratings, suitable for high-power applications. Moderate switching speed, faster than traditional SCRs, but slower than some other semiconductor devices like IGBTs. High dV/dt capability, able to handle high rates of voltage change without unintentionally turning on. Applications: inverters and converters, used in power inverters and DC-DC converters where controlled switching is essential. Motor drives, employed in variable speed motor drives and industrial motor control applications. Power supplies, found in switch mode power supplies and uninterruptible power supplies, UPS. HVDC transmission, used in high voltage direct current, HVDC, transmission systems for efficient long-distance power transfer. Advantages: active turn-off capability. Unlike SCRs, GTOs can be turned off by a gate signal, providing better control over power switching. High power handling, can manage large currents and voltages, making them suitable for high-power applications. Reduced need for commutation circuits. The ability to turn off using a gate signal simplifies circuit design compared to SCRs that require external commutation circuits. Limitations: gate drive complexity. Requires a complex gate drive circuit to supply the necessary turn-off current. Heat management. Generates more heat during switching, requiring efficient cooling solutions. Slower switching speed. Although faster than SCRs, GTOs are slower compared to modern semiconductor devices like IGBTs and MOSFETs. The GTO's ability to be actively turned off by a gate signal makes it a versatile component in power electronics, offering advantages in applications where controlled switching of high power is required. A triode for alternating current, is a type of thyristor used to control AC power. Unlike an SCR, which is unidirectional, a triac can conduct current in both directions when triggered. This makes it especially useful for AC applications where bidirectional control is required. Structure and operation. Structure. Layers. The triac is a 4-layer semiconductor device with a 6-layer structure, PNP, effectively combining 2 SCRs in antiparallel. Terminals. It has 3 terminals. Main terminal 1, MT1 connected to one end of the device. Main terminal 2, MT2 connected to the other end of the device. Gate, G connected to the control terminal. Operation, off state, blocking state. When no gate signal is applied, the triac remains in a high impedance state, blocking current flow between MT1 and MT2. On state, conducting state. When a gate signal is applied, the triac switches to a low impedance state, allowing current to flow between MT1 and MT2. It can be triggered into conduction by a gate pulse of either polarity applied to the gate terminal with respect to MT1. The triac continues to conduct until the current drops below a certain threshold, known as the holding current. Key characteristics: bidirectional conduction, can conduct current in both directions, making it ideal for AC applications. Single gate control, requires only a single gate signal to trigger conduction in either direction. Latching device, remains in the conducting state once triggered until the current falls below the holding current. Sensitivity to dV/dt, requires careful circuit design to prevent false triggering due to rapid voltage changes. Applications: AC power control, commonly used in light dimmers, fan speed controls, and heater controls. Motor control, employed in controlling the speed of AC motors in various appliances and industrial applications. Phase control, used in phase control circuits for adjusting the power delivered to a load. Switching applications, suitable for general-purpose switching of AC loads. Advantages: bidirectional switching, simplifies circuit design for AC applications by allowing control of current flow in both directions with a single device. Compact design, combines the functionality of 2 SCRs into a single component, reducing the need for additional components. Cost-effective, provides an economical solution for controlling AC power in various applications. Limitations: dV/dt sensitivity, requires careful design to avoid false triggering due to high rates of voltage change. Limited switching speed, slower switching compared to other semiconductor devices like MOSFETs and IGBTs. Higher gate current, requires a higher gate current for triggering compared to some other thyristor types. Typical triggering quadrants. The triac can be triggered in 4 quadrants, depending on the polarity of the voltage across MT1 and MT2 and the polarity of the gate signal. Quadrant I, MT2 positive, gate positive with respect to MT1. Quadrant 2, MT2 positive, gate negative with respect to MT1. Quadrant 3, MT2 negative, gate negative with respect to MT1. Quadrant 4, MT2 negative, gate positive with respect to MT1. Understanding the characteristics and operation of triacs is essential for designing effective AC power control circuits, enabling precise control over power delivery in a wide range of applications. A diac, diode for alternating current, is a bidirectional trigger device that is commonly used to trigger triacs. It is a semiconductor device that conducts current only after its breakover voltage is exceeded, regardless of the polarity of the voltage applied across its terminals. This makes it useful in AC applications for providing symmetrical triggering signals. Structure and operation. Structure. Layers. The diac is typically a 5-layer structure with a PNP configuration, similar to 2 diodes connected in series but in opposite directions. Terminals. It has 2 terminals, usually referred to as A1 and A2, or simply as the main terminals. Operation. Off state, blocking state. When the voltage across the diac is below its breakover voltage, V_BL, it remains in a high impedance state, blocking current flow. On state, conducting state. When the voltage across the diac exceeds its breakover voltage, it switches to a low impedance state, allowing current to flow. The diac will conduct until the current drops below a certain holding value, at which point it returns to the off state. Key characteristics. Bidirectional conduction. Can conduct current in both directions once the breakover voltage is exceeded. Breakover voltage, a characteristic voltage threshold above which the diac conducts. This is typically around 30-50 V for most diacs. Switching behavior provides a sharp transition from the off state to the on state, making it useful for triggering other devices like triacs. Applications. Triggering triacs. Commonly used in circuits to provide a consistent and symmetrical trigger signal for triacs in AC applications. Phase control, used in light dimmers, fan speed controllers, and other phase control applications to control the phase angle of the AC supply. Overvoltage protection, can be used to protect circuits by clamping overvoltage transients. Advantages. Symmetrical operation, provides consistent triggering in both directions of AC current, ensuring balanced operation. Simplicity, simple and reliable operation without the need for a gate signal. Cost-effective, provides an economical solution for triggering and protection applications. Limitations. Fixed breakover voltage. The breakover voltage is fixed and cannot be adjusted, which may limit its application in some circuits. Limited current capacity, not suitable for handling large currents, mainly used for triggering purposes. Example circuit, light dimmer. In a light dimmer circuit, the diac is often used in conjunction with a triac. Here's how it works. RC network. An RC, resistor capacitor, network is used to delay the phase of the AC voltage. Triggering the diac. When the voltage across the capacitor exceeds the diac's breakover voltage, the diac conducts. Triggering the triac. The current through the diac provides a gate pulse to the triac, turning it on. Controlling power. By adjusting the resistance in the RC network, the phase angle at which the diac triggers can be controlled, thus adjusting the power delivered to the load, e.g., a light bulb. Understanding the operation and characteristics of diacs is crucial for designing efficient AC power control circuits, especially those involving triacs for phase control applications. The silicon-controlled switch, SCS, is a type of thyristor similar to an SCR but with additional control features, allowing it to be both turned on and off by gate signals. This makes it more versatile and useful in various switching applications where precise control is required. Structure and operation. Structure. Layers. The SCS has a 4-layer PNP structure, similar to an SCR. Terminals. It has 4 terminals. Anode, A connected to the outer P-type layer. Cathode, K connected to the outer N-type layer. Gate, G1 connected to the inner P-type layer, used for turning on the SCS. Gate, G2 connected to the inner N-type layer, used for turning off the SCS. Operation. Off state, blocking state. When no gate signal is applied, the SCS remains in a high impedance state, blocking current flow from the anode to the cathode. Turn on. To turn on the SCS, a positive gate current is applied to G1. This initiates the conduction process, allowing current to flow from the anode to the cathode. The SCS behaves similarly to an SCR in the on state, maintaining conduction even after the gate signal is removed, as long as the current through the device remains above the holding current. Turnoff. To turn off the SCS, a positive gate current is applied to G2. This removes carriers from the junctions, interrupting the current flow and turning the device off. Key characteristics. Bidirectional gate control can be turned on with a gate signal at G1 and turned off with a gate signal at G2. Latching device remains in the conducting state once triggered until an off signal is applied. High voltage and current ratings, suitable for applications requiring control of large amounts of power. Gate sensitivity requires specific gate currents for turning on and off. Applications. Switching applications, used in circuits where precise control of turning on and off is required. Pulse circuits, employed in pulse generation and timing circuits. Counters and registers, utilized in digital circuits such as counters and shift registers. AC and DC motor controls, used for controlling the operation of motors in industrial applications. Advantages. Active turn-off capability. Unlike SCRs, SCSs can be actively turned off by a gate signal, providing better control over power switching. High power handling. Can manage large currents and voltages, making them suitable for high-power applications. Simplified control. Provides more straightforward control compared to using separate circuits for turning off SCRs. Limitations. Gate drive complexity. Requires a complex gate drive circuit to supply the necessary turn-on and turn-off currents. Heat management. Generates more heat during switching, requiring efficient cooling solutions. Slower switching speed. Although faster than traditional SCRs, SCSs are slower compared to modern semiconductor devices like IGBTs and MOSFETs. Example application. Pulse generation circuit. In a pulse generation circuit, the SCS can be used as follows. Initial state. The SCS is in the off state, blocking current flow. Turn on pulse. A positive pulse is applied to G1, turning on the SCS and allowing current to flow. Pulse output. The SCS conducts and provides an output pulse. Turn off pulse. A positive pulse is applied to G2, turning off the SCS and stopping the current flow. Repeat. The cycle can be repeated to generate a series of pulses. Understanding the operation and characteristics of SCSs is essential for designing circuits that require precise control over switching, making them valuable components in various power and digital applications. The light-activated silicon-controlled rectifier, LASCR, is a type of thyristor that can be triggered by light instead of an electrical gate signal. This feature makes it particularly useful in applications where electrical isolation and remote triggering are required. Structure and operation. Structure. Layers. The LASCR has a 4-layer PNPN structure, similar to a conventional SCR. Terminals. It has 3 main terminals. Anode, A connected to the outer P-type layer. Cathode, K connected to the outer N-type layer. Gate, G connected to the inner P-type layer. This can also be used for electrical triggering if needed. Operation. Off state, blocking state. When no light or gate signal is applied, the LASCR remains in a high impedance state, blocking current flow from the anode to the cathode. Light activation. When light of sufficient intensity falls on the LASCR, it generates electron-hole pairs in the semiconductor material. This reduces the barrier potential and initiates the conduction process, turning the device on. Once triggered, the LASCR remains in the conducting state, allowing current to flow from the anode to the cathode, similar to a conventional SCR. Turn off. The LASCR can be turned off by reducing the current through the device to below the holding current, similar to an SCR. Key characteristics. Optical triggering. Can be triggered by light, providing electrical isolation between the control signal and the device. High voltage and current ratings. Suitable for high-power applications. Latching device. Once triggered, it remains in the conducting state until the current drops below the holding current. Gate sensitivity. Can also be triggered electrically through the gate terminal if needed. Applications. Opto-isolation. Used in circuits requiring electrical isolation between the control and power stages. Remote switching. Suitable for remote control applications where electrical signals might not be feasible. Overvoltage protection. Provides protection by triggering in the presence of excessive light, e.g., lightning strikes. AC and DC power control, employed in various power control applications where optical triggering is advantageous. Advantages: electrical isolation. Optical triggering ensures isolation between control and power circuits, enhancing safety and reliability. Remote operation can be triggered remotely without the need for electrical connections. High sensitivity can be triggered by relatively low levels of light, making it suitable for sensitive applications. Limitations: light sensitivity requires a light source for triggering, which may add complexity to the system design. Environmental factors: sensitivity to ambient light and potential need for shielding or filtering to prevent false triggering. Heat management: like other thyristors, lascars generate heat during operation and require proper cooling solutions. Example application: remote light-activated switch. In a remote light-activated switch application, the LASCR can be used as follows. Initial state: the LASCR is in the off state, blocking current flow. Light trigger: a light source, e.g., LED or laser, is activated, illuminating the LASCR and triggering it into conduction. Current flow: the LASCR conducts, allowing current to flow and powering the load, e.g., motor, lamp. Turnoff: the current through the LASCR is reduced below the holding current, turning off the device. Understanding the operation and characteristics of lascars is crucial for designing circuits that require optical triggering and electrical isolation, making them valuable components in various power control and protection applications. The integrated gate commutated thyristor, IGCT, is a type of thyristor that combines the characteristics of gate turnoff thyristors, GTOs, and insulated gate bipolar transistors, IGBTs. It is designed for high-power applications where efficient and reliable switching is required. Structure and operation. Structure. Layers. The IGCT has a complex structure similar to a GTO, but it incorporates features that allow for faster switching and better control. Terminals. It has three main terminals. Anode, A connected to the outer P-type layer. Cathode, K connected to the outer N-type layer. Gate, G connected to the control terminal, typically integrated with a drive circuit. Operation. Turn on. When a gate signal is applied, the IGCT turns on, allowing current to flow from the anode to the cathode. The gate drive circuit is designed to provide a high current pulse to switch the device on rapidly. Turn off. The IGCT can be turned off by applying a reverse gate current. This current removes carriers from the junctions, turning off the device. The turn-off process is very fast due to the low inductance path of the gate drive circuit, which quickly commutates the current. Key characteristics. High power handling. Can manage very high currents and voltages, making it suitable for high-power applications. Fast switching. Faster than traditional GTOs due to the integrated gate drive circuit and low inductance design. High efficiency. Low on-state voltage drop and efficient switching reduce power losses. Robust design. Can handle high D/dt, rate of change of current, and dV/dt, rate of change of voltage, without false triggering. Applications. Medium and high voltage inverters. Used in medium and high voltage inverters for industrial applications, such as motor drives and traction systems. HVDC transmission. Employed in high voltage direct current, HVDC, transmission systems for efficient power transmission over long distances. Renewable energy systems. Integrated into systems like wind and solar power converters to handle large power flows. Industrial drives. Used in various industrial drive applications requiring precise control and high reliability. Advantages. High power capability. Suitable for applications requiring the handling of large amounts of power. Fast switching. Provides faster switching than traditional thyristors, improving efficiency and performance. Integrated gate drive. Simplifies circuit design and improves reliability by integrating the gate drive circuit. Low inductance. The low inductance design of the gate drive circuit reduces switching losses and improves performance. Limitations. Complex gate drive requirements. Requires a specialized gate drive circuit capable of providing high current pulses for switching. Thermal management. Generates significant heat during operation, requiring effective cooling solutions. Cost. Typically more expensive than simpler thyristors like SCRs or standard GTOs due to the complexity of the device and its drive circuitry. Example application: high-power industrial motor drive. In a high-power industrial motor drive application, the IGCT can be used as follows. Initial state: the IGCT is in the off state, blocking current flow. Turn-on pulse: a high current pulse is applied to the gate, turning on the IGCT and allowing current to flow to the motor. Current flow: the IGCT conducts, providing power to the motor and controlling its operation. Turn-off pulse: a reverse gate current is applied to turn off the IGCT, stopping the current flow to the motor. Control: the gate drive circuit continuously monitors and adjusts the gate signals to control the motor's speed and torque precisely. Understanding the operation and characteristics of IGCTs is essential for designing high-power electronic systems that require reliable and efficient switching, making them valuable components in various industrial and power transmission applications. The MOS-controlled Thyristor, MCT, is a type of thyristor that combines the features of a conventional thyristor with the control capabilities of a metal oxide semiconductor field effect transistor, MOSFET. This hybrid device offers advantages in terms of control and switching performance, making it suitable for high-power and high-speed applications. Structure and operation. Structure. Layers. The MCT has a 4-layer PNP structure like a traditional thyristor, but it also incorporates MOSFET structures for enhanced control. Terminals. It has 3 main terminals. Anode, A connected to the outer P-type layer. Cathode, K connected to the outer N-type layer. Gate, G connected to the MOSFET gate structure. Operation. Turn on. To turn on the MCT, a positive voltage is applied to the gate terminal relative to the cathode. This creates an inversion layer in the MOSFET structure, allowing current to flow from the anode to the cathode. Turn off. To turn off the MCT, a negative voltage is applied to the gate terminal relative to the cathode. This depletes the inversion layer, stopping the current flow and turning off the device. The MOSFET control allows for precise and rapid switching. Key characteristics. High power handling. Can manage high currents and voltages, making it suitable for high-power applications. Fast switching. The MOSFET control structure allows for faster switching than traditional thyristors. Efficient control. Combines the high-power capability of a thyristor with the ease of control of a MOSFET. Latching device. Once turned on, it remains in the conducting state until actively turned off by the gate signal. Applications. Motor control. Used in AC and DC motor control systems, offering precise control over motor operation. Power converters. Employed in various power conversion applications, including inverters and DC-DC converters. Induction heating. Suitable for induction heating systems due to its high power handling and fast switching capabilities. Industrial automation. Used in industrial automation systems where reliable and efficient power control is required. Advantages. High power and fast switching. Combines the high power capabilities of thyristors with the fast switching of MOSFETs. Efficient control. Offers precise control over switching, improving the performance and efficiency of power systems. Simplified drive circuit. Easier to control than traditional thyristors, reducing the complexity of the gate drive circuitry. Bidirectional control. Can be designed to handle bidirectional current flow, making it versatile for various applications. Limitations. Complex structure. More complex than traditional thyristors, leading to higher manufacturing costs. Thermal management. Generates heat during operation, requiring effective cooling solutions. Gate drive requirements. Requires a specialized gate drive circuit capable of providing the necessary control signals. Example application: variable frequency drive, VFD. In a variable frequency drive, VFD, application, the MCT can be used as follows. Initial state. The MCT is in the off state, blocking current flow. Turn-on signal. A positive gate voltage is applied, turning on the MCT and allowing current to flow to the motor. Motor control. The MCT conducts, providing power to the motor and controlling its speed by adjusting the frequency of the AC supply. Turn-off signal. A negative gate voltage is applied to turn off the MCT, stopping the current flow to the motor. Precise control. The gate drive circuit continuously monitors and adjusts the gate signals to precisely control the motor's speed and torque. Understanding the operation and characteristics of MCTs is crucial for designing high-power electronic systems that require efficient and precise control, making them valuable components in various industrial and power applications. Thyristors are semiconductor devices known for their ability to switch and control large amounts of electrical power. Here are the key characteristics that define thyristors. Unidirectional conduction. Thyristors conduct current in only one direction, from anode to cathode, once triggered. This characteristic makes them suitable for rectification and AC power control applications. Latching. Once triggered into conduction, thyristors remain in the conducting state even after the triggering signal is removed. They stay latched until the current through them drops below a certain threshold called the holding current. Triggering. Thyristors require a specific trigger signal to turn on, commence conduction. The triggering can be achieved by applying a gate current in the case of devices like SCRs, GTOs, and MCTs, or by other means such as light enlaskers or voltage and diodes. Turn-off methods. Turning off thyristors typically involves reducing the current through them below the holding current. Some types, like GTOs and MCTs, can be turned off by applying a specific gate signal or voltage. Voltage ratings. Thyristors are designed to handle high voltages. They are available in various voltage ratings suitable for different applications ranging from a few volts to several kilovolts. Current ratings. They can handle large currents, making them suitable for high-power applications such as motor drives, power supplies, and industrial controls. Switching speed. Thyristors generally have slower switching speeds compared to other semiconductor devices like MOSFETs and IGBTs. However, newer types such as IGCTs and MCTs offer faster switching capabilities than traditional SCRs and GTOs. Heat dissipation. Thyristors generate heat during operation due to conduction losses. Effective heat dissipation methods such as heat sinks and cooling systems are essential to ensure reliable operation and longevity. Application-specific types. There are various types of thyristors tailored for specific applications. SCR. Silicon-controlled rectifier mainly used for rectification and AC power control. GTO, gate turn-off thyristor offers the ability to turn off by applying a gate signal, enhancing control over switching. MCT, MOS-controlled thyristor combines characteristics of thyristors with MOSFET control for improved switching speed and efficiency. IGBT, insulated gate bipolar transistor. Though not a thyristor, it operates similarly in some applications, offering fast switching and low conduction losses. Thyristors are fundamental components in power electronics, providing robust solutions for controlling and switching electrical power in industrial, commercial, and consumer applications. Understanding their characteristics is crucial for selecting the right type for specific design requirements. Understanding the various types of thyristors and their characteristics is crucial for selecting the right device for specific power control applications.